Hello. Today we're going to talk about word problems that involve quadratic functions. In these kinds of problems, the key words to look for are maximum or minimum. But how do you find a maximum or minimum value? Let's look at the standard form of a quadratic function. F of x equals a times x minus h quantity squared plus k. The graph of this function will be a U-shaped curve called a parabola. If the a is a positive constant greater than 0, the parabola will open up, and f of h, which equals k, will be the minimum value of the function. Notice that if you substitute h for the x in this equation, you're going to have f of h is a times h minus h squared. H minus h would be 0. 0 squared is 0 plus k. So when you substitute an h for the x into the equation, the value of the function at x equals h is equal to k. If the a is a negative number, the parabola will open down, and in that case, f of h, which equals k, will be the maximum value of the function. The point hk on the graph of this quadratic function is called the vertex of the parabola. You might ask yourself, why is hk the vertex? Why is it a minimum if a is positive? Why is it a maximum if a is negative? Let's understand this by looking at two cases. In case one, let's suppose that a is positive. Then the expression x minus h, the quantity squared, is always going to be greater than or equal to 0. Why? No matter what value x has, any expression squared has to be greater than or equal to 0. If this expression is 0, 0 squared is 0. If this expression is anything other than 0, when you square it, you get a positive number. Now, taking this inequality, let's multiply both sides by a positive number a. If you multiply an inequality through by a positive number, you do not reverse the direction of the inequality. So a times x minus h squared is going to be greater than or equal to a times 0, but a times 0 is still just 0. Finally, let's add k to both sides of this inequality. A times x minus h squared plus k is going to be greater than or equal to 0 plus k, which is k. The a times x minus h squared plus k is your y, or your f of x. And we see here then that this means k is the minimum value of y, since y is always greater than or equal to k. And this expression is going to equal k when the x value is equal to h. Looking at case 2, suppose a is a negative number. Again, x minus h squared has to be greater than or equal to 0, no matter what value x takes on. But now, when we multiply the inequality through by a negative number, a times x minus h squared is going to be less than or equal to 0 times a, which would still be 0. When you multiply an inequality through by a negative number, you reverse the direction of the inequality. Now we can add k to both sides of this inequality. We'll have a times x minus h squared plus k is less than or equal to 0 plus k, which is just k. This expression is our y, and so now we have y is always less than or equal to k. That would mean that k is the maximum value of y, and it occurs when the x equals h. What is the relationship between the two forms of equations for a quadratic function that you've encountered so far in this college algebra course? Recall that earlier we talked about ax squared plus bx plus c as a quadratic function, and we found the places where it had x-intercepts or complex zeros. Now we are saying we're going to write quadratic functions in the form of a times x minus h, the quantity squared, plus k. If we want to see how the h and the k are related to these coefficients a, b, and c, we want to set the two forms for expressing a quadratic function equal to each other. On the right-hand side, let's multiply x minus h squared out by taking x minus h times x minus h and using FOIL. That would give us x squared minus 2hx plus h squared. And that whole expression is multiplied by a, and then we have a plus k on the end. When we distribute the a, we get ax squared minus 2ah times x plus a times h squared plus k. And that has to always equal ax squared plus bx plus c for all values of the variable x. Notice that a is the coefficient of the x squared on the left, and a is the coefficient of x squared on the right. That means the a in the ax squared plus bx plus c is always going to be the same number as the a in the form a times x minus h squared plus k. Also notice that on the left, the coefficient of x is b, and on the right, the coefficient of x is minus 2ah. If this equation is to hold for all values of x, that means that the b has to equal the minus 2ah. If we solve this equation for h, we see that h is always going to equal minus b over 2a. So in other words, if you're given the equation of a quadratic function in the form y equals ax squared plus bx plus c, the x-coordinate of the vertex will be given by h equal to minus b over 2a. To find k, the y-coordinate of the vertex, you just substitute the value for h into the expression for the quadratic function. So k will equal f of minus b over 2a. Let's apply this now. In word problems that involve a quadratic function as a model for a real-life situation, we want to look for the keywords maximum or minimum. Those words in that type of problem are the indication that you need to find the vertex. Here's an example. A rancher wants to enclose a rectangular corral adjacent to a river. He will use exactly 180 total yards of fencing on 3 sides of the corral, but no fencing will be needed along the river. So let's say that this dimension of his rectangular corral will be represented by x. The opposite side of the rectangle then would also be x, and we will call the side adjacent to x, or in other words, the side parallel to the river, to be y. Since he is going to use exactly 180 total yards of fencing, we know that x plus y, or in other words, 2x plus y, has to equal 180 yards, and therefore y has to be 180 minus 2x. The area of this rectangle is x times y, but if we substitute 180 minus 2x for the y, we get that the area as a function of x is x times 180 minus 2x in parentheses. If you multiply that out and rearrange the order of the terms, you get minus 2x squared plus 180x. This is a quadratic function then. If I want to know what dimensions should be used in order to maximize the area, there's that keyword maximize. I have a quadratic function. I'm looking to maximize something. So I am looking for the vertex. I set x equal to minus b over 2a. In this problem, the a is -2 and the b is 180. So I have minus 180 over 2 times -2. That works out to be 45. If x equals 45, the y is 180 minus 2 times 45, and that works out to be 90. So I want x to be 45 yards and y to be 90 yards in order to maximize the area of the corral when I can use only 180 total yards of fencing. If you want to know what is the maximum area, you just substitute 45 for the x into the function for the area. Or alternatively, since we know the area is x times y, and we've already found that y is 90, 45 times 90 would give me 4,050 square yards for the maximum area. Here's another example. The Cheerful Thoughts gift shop in the lobby of Mercy Hospital currently sells 60 pounds of fudge per month and charges $7 per pound. Market research indicates that for every $1 increase in the price per pound of the fudge, the gift shop will sell 10 fewer pounds of fudge per month. And for every $1 decrease in the price of a pound of fudge, the gift shop will sell 10 more pounds of fudge per month. Let's let P be the price of a pound of fudge and let N equal the number of pounds of fudge sold per month. Suppose we want to find and simplify an expression to represent N as a linear function of the price. Remember that the number of pounds sold is dependent on the price. So price is our independent variable, the first in our ordered pair, and N is the dependent variable. Instead of X and Y, we're using P and N. But the principle of finding a linear equation works exactly the same way. We know that we do want a linear function because the number of pounds is changing at a constant rate with the change in the price. From the given information, the change in the number of pounds, change in N, over the change in P or change in price is calculated as this. If the price goes up $1, the number of pounds goes down 10, so minus 10 over plus 1. Or if the price is decreased by $1, the number of pounds increases by 10, plus 10 over minus 1. Negative 10 over plus 1 or plus 10 over negative 1 both equal minus 10. So the linear model will have a slope of minus 10. We're given an ordered pair in the problem. A price of $7 corresponds to 60 pounds. So 7, 60 is an ordered pair that is on the graph of this linear function. If we use the point slope form of a linear equation, we're going to have N minus 60 equals the slope, negative 10, times the price P minus 7. If you multiply that out and solve for N, you get N is equal to minus 10P plus 130. Considered as a function, N as a function of P, the number of pounds as a function of the price, is equal to minus 10P plus 130. Now, let's let R represent the gross monthly revenue of the gift shop from the sale of fudge. We want to write and simplify an expression that represents R as a function of P. The revenue is the price per pound times the number of pounds sold. So it's P multiplied by N, but N, we've just seen, is minus 10P plus 130. When I multiply that out, I get minus 10P squared plus 130P. So the revenue as a function of the price is a quadratic function. Suppose I want to know What value of P makes R a maximum? If I am the owner of this gift shop, I want to set the price of the fudge to maximize my revenue. So I'm going to set P equal to minus B over 2A. In this problem, A is -10 and B is 130. So minus B over 2A would be minus 130 over 2 times minus 10. If you work that arithmetic out, it's 6.5 or $6.50. That would be the price I want to charge per pound of fudge to maximize my revenue. What would be this maximum revenue? I plug $6.50 into the revenue function, where the revenue is a function of the price, and I have minus 10. The price is $6.50 squared plus 130 times $6.50. When you work out that arithmetic, it works out to $422.50 revenue per month. How many pounds of fudge will the gift shop sell at this price? We go back to our linear function and substitute $6.50 for the price. We have minus 10 times $6.50 plus 130. And if you work that arithmetic out, it turns out to be 65 pounds of fudge. Here's a final example. If a ball is thrown directly upward with a velocity of 40 feet per second, its height in feet after t seconds is given by the function h of t equals 40t minus 16t squared. When will the ball attain its maximum height, and what will that maximum height be? Again, we have a quadratic function. We have this keyword maximum, so we are looking for the vertex. I can rearrange the order of these terms. H of t is minus 16t squared plus 40t. So in this problem, A is minus 16 and B is 40. To find the time at which the ball reaches its maximum height, I set t equal to minus b over 2a. In this problem, that's minus 40 over 2 times minus 16. That arithmetic works out to be 5/4 or 1.25 seconds. To find the height of the ball at the maximum point, I substitute 1.25 for the t into the quadratic function. Minus 16 times 1.25 squared plus 40 times 1.25 works out to be exactly 25 feet. So the ball will attain a maximum height of 25 feet, 1.25 seconds after it is thrown. Hopefully this helps you see that word problems involving a quadratic function are not scary at all. Just recall that the maximum or minimum values are going to occur at the vertex, and you have an easy way to find the coordinates of the vertex.